All right, so now we're going to, again, just scratch the surface on rational functions. So a rational number is any number that can be written as a fraction. So for instance, 3 can be written as a fraction as 3 over 1. Move this. 0.5 can be written as 5 over 10 or 1/2. So a rational is just something that can be written as a fraction. Well, when we're dealing with rationals or fractions, so like the fraction or the rational function 1 over x, remember you cannot have 0 in the denominator. If you have 0 in the denominator, what you end up with, denominator, so the bottom, what you have is an undefined term, right? We cannot have 0 in the bottom. Doesn't work. So with any rational, which just means any fraction, what you want to do is you want to identify what's the one number that restricts, that is restricted in the domain. In other words, what's the one number that x can't be? So when you're looking at a rational function and you are looking for the domain restriction, right? The domain restriction means what's the one number that will make this bottom 0. It's fine to have 0 in the top. If you have 0 in the numerator, it just means the whole thing goes to 0. Where the restriction lies is in the denominator. So what you're going to do is you're going to set the denominator to not equal 0. So in other words, this denominator cannot be 0. Okay? And then you just solve like normal. So we're going to add 6 to both sides. So x cannot be 6. Okay? Now you're going to write this in interval notation. So the way that I like to show it is do a number line. X cannot be 6. It can be everything above it, and it can be everything below it. So if you look at a graph, you go, oh, okay, that makes more sense. So in interval notation, it's all the numbers, negative infinity to 6, and it is a parenthesis because it does not include 6. And then you're going to use the union symbol, which just means and. That's all that means. And then from 6, and again, we're not including 6, to infinity. Okay, so it's all the numbers below 6, all the numbers above 6. Just can't be 6. All right, so that is how you're going to find the domain. So this is my domain. Then the other question says is find the vertical asymptote. Well, if I take you back to this function, if you have the function, it's a rational function, 1 over x, the base function, the base graph looks something like this. And then I can shift it. I can shift it all over. Well, what you notice is this graph gets close and closer and closer and closer to my y-axis, but it never crosses it. Up here, it gets closer and closer and closer to the y-axis again, but it doesn't cross it. Where it approaches but doesn't cross, that is what's called a vertical asymptote. Okay, big word. All it means is it approaches this vertical line, but it won't cross it and it won't touch it. So when you're looking for the vertical asymptote, what that means is you're looking for the domain restriction. So the vertical asymptote is x equals 6. So if I were to graph this particular function at x equals 6, I would have an invisible vertical asymptote, and my graph would do something like this. Still the same basic shape, but it has been shifted over to where the vertical asymptote of x equals 6 is now comes into play. All right? So when you're working with a rational expression, just remember you can't have 0 in the bottom. So you set the denominator to 0 or to not equal 0, and you factor. Okay? So let me do a couple more examples. So this is page 85 in your packet. So I just did number 1. So now let me do number 2. So number 2 says 2x plus 5 over x squared minus 6x minus 16. Okay, so now we have a trinomial. So now you have to remember how to factor a trinomial. So again, the top doesn't matter. You don't have to do anything to the top when finding vertical asymptote or domain. The bottom is what you are setting to 0. So we're going to have x squared minus 6x minus 16 cannot equal 0. And now you're going to use your factoring techniques. So negative 16, what do you multiply to get negative 16? And what do you add to get negative 6? So the factors of 16, 1 and 16, 2 and 8, 4 and 4. You know that to multiply to get a negative, one of these values have to be negative. Since our bottom number is negative, that tells me that my larger numbers are going to be negative. Now, when I add 1 plus a negative 16, I get negative 15. Doesn't match. 2 and negative 8, that's where I get my negative 6. So now I come back over here, and I have x plus 2, x minus 8 equals 0. And because there's a 1 in here, I can just go right from my factors right into my polynomial. And now I'm going to set each to 0 and solve. So here I'm going to subtract 2, so I get x equals negative 2, or doesn't equal negative 2. Here I'm going to add 8, so I get x cannot be positive 8. Okay, now number lines always help when you're looking for the domain. So I get negative 2 and positive 8. I know my values cannot be negative 2 or 8. I can be all the numbers below 8 or below negative 2, all the numbers in between negative 2 and 8, and all the numbers above 8. So drawing a graph actually gives you a visual so that when you write out your domain, it actually allows you to see it. So I have all values from negative infinity to negative 2, parenthesis, and between negative 2 and 8, and from 8 to infinity. And that's your domain restriction in interval notation. All right, let me try one more, and then I'm going to show you an application. So the applications aren't too bad. You're given the rational, and then you're just going to plug the values in. Okay, so this is number 7 on page 85. So we have a function equals 6x plus 36 all over 3x squared plus 5x minus 50. Okay. All right, so don't care about the top. All we're doing is setting the denominator to not equal 0 to find our domain. Okay, this I can't factor anything out, so I have a number in front, so I'm going to use my AC method. 3 times negative 50 is negative 150. When I add, I get 5. Factors of negative 150. I know I only have to be 5 steps away, so I can do 5 times 30. I can do 10 times 15. Okay, and that's it. So because it's negative, one of them has to be negative. This is a positive value, so my larger numbers are positive, which makes my smaller numbers negative. So negative 10 plus 15 is 5. Negative 10 times 15 gives me a negative 150. So again, this AC method, what you're doing is you're going from a trinomial and you're going to rewrite it as a 4-term polynomial. Now, remember, even though I wrote it negative 10 first, 15 second, I can flip-flop those because I saw that 15 and 3 have more in common than 10 and 3. So I just rearranged it. I still have 5x. 15x minus 10x still gives me 5x. So now I'm going to do factoring by grouping. So factor out of 3x. I have x plus 5 left. Use this middle sign. Factor out a 10. And I still have x plus 5 in the middle. All right? And if you want proof, negative 10 times x is negative 10x. Negative 10 times 5 is a negative 50. So now I'm going to factor out what's in common of x plus 5. What's left goes in the other set of parentheses. Okay, and now I'm going to set it to 0. Can't, remember, it's can't equal 0. My pen is starting to die. And now I'm going to solve for both. So x plus 5 cannot be 0. 3x minus 10 cannot be 0. So x cannot be negative 5, subtracting 5 from both sides. This one is a two-step equation, so I'm going to add 10 to both sides. So I have 3x equals 10, and then I'm going to divide both sides by 3. So I get x cannot be 10/3. Okay? So now, to get my domain, so I'm going to make my number line. I have a negative 5 and a positive 10/3. 10/3, if you want to change it to a whole number, is 3 1/3. Okay, so I know it can't be negative 5, but it can be everything below it. It can't be 10/3, everything in between, and everything above. So my domain is negative infinity to negative 5, and between negative 5 and 10/3, and between 10/3 and infinity. Now, one thing that I forgot to talk about with number 2, and I'll talk about it here, is we found the domain restrictions. You also found the vertical asymptotes. So going back to number 2, the vertical asymptote is x equals 8 and x equals negative 2, exactly what our domain was for this one. Our vertical asymptote is x equals negative 5 and x equals 10/3. So your domain restrictions coincide exactly with your vertical asymptotes. That tells you where the graph cannot cross. And that's the rationals. So now what we're going to do is now we're going to actually use a rational and do an application. So the application of a rational function, these are pretty basic ones. We're not gonna do more than scratch the surface on these. So this is number 8 on page 86. So you have a function equals 90 divided by 100 minus p. Okay, so let me give you the pertinent information. The s function estimates, this is a model that estimates the number of sunflowers, so this is sunflowers, needed to remove p%, this is a percent, of contamination. So here's what happens. Farmers can go in and plant certain products or certain plants that will draw the contaminants out of the soil. Okay, so that's the scenario of this. So the first question is, how many sunflowers would it take to remove 50%, I'm writing the page number and what number I'm working on. How many sunflowers would it take to remove 50% of the contamination? Now, this number S is in thousands. It's important to know what your number represents. Okay, now sometimes what they'll do is they'll take a bunch of zeros off and it's much easier to work with. So if we want to remove 50% of the contamination, notice P is already in the percent, so you don't have to change it to a decimal. So if we're removing 50% of the contamination, I'm just going to put in 50. So this is S of 50 equals. And then I get 90 over 50, which becomes 1.8. That's the answer that your calculator is going to come up with. But remember, this answer, this is our number of sunflowers when we're removing 50% of the contaminants, is in thousands. So what you're going to do is you're going to move this decimal point over 3 times because thousands has 3 zeros. So you need 1,800 sunflowers to remove 50% of the contaminants. Okay? Then B says, how many sunflowers would it take to remove 99% of the contamination? So I want 99%. So 90 divided by 100 minus 99 equals 90 over 1. So the number of sunflowers that I need to plant in order to have 99% contamination removed is a 90. So remember, we're moving our decimal point over 3 places because it is in thousands. So I need 90,000 sunflowers to remove 99% of the contaminants, okay? And then the last question says, what percent removal cannot be achieved? Well, anytime you're looking for what can't happen, you go back to here, remember the denominator, and you find out, all right, what's the one number that will make this denominator 0? Well, if you solve for p, you get negative 100. You bring your 100 over. Then I'm going to divide by negative 1. So you cannot have 100% of your contaminants removed. All right? 100% would make this a 0. Undefined. Won't happen. So that's where you go back to when you have a rational expression or a function. What's going to make this denominator 0? Okay? So you cannot remove 100% of the contaminants. Okay, so let's do number 9 real quick, and then that will be it for, that's all you have to remember or know how to do when you get to the rational functions. Okay, so this is number 9. So our function is cost. So this is in terms of the Northwest Vista campus's pond. And we're talking about what would it cost to remove X tons of pollution. So C of X represents cost in hundreds. So hundreds of dollars. So now you're going to move your decimal point twice because there's 2 zeros in 100. And X is, this is tons of pollution. Okay, so we're going to use that function. So the first question says, how much would it cost to remove half a ton of pollution? So we're going to remember X represents number of tons. So half a ton. So 70 times 0.5 is 35. 2 minus 0.5 is 1.5. 35 divided by 1.5, you get 23.3333. So going back to that the cost is in hundreds, what you're going to do is you're going to take your decimal and you're going to move it twice. So it's going to cost $2,333 to remove half of the pollutants in the NVC pond. And then B says, explain what happens if NVC attempts to remove all 2 tons of pollution. So if I plugged a 2 in here and here, I'd end up with 70 times 2 over 2 minus 2. So I'd end up with 140 over 0. So what that tells you is you cannot remove all 2 tons because it would make it undefined. So what it means is that the cost is an infinite amount. Okay, the cost there's no stopping point with the cost if you try to remove all of the pollutants. Okay, that's rational functions.